Okay, with that, I think we'll move into the panel session. Folks are welcome to continue to present, to ask any questions that they'd like the panelists to discuss through the chat window. Just to keep logistics simple, I'll see how I can collect the questions and ask the panelists as we go forward. So for the panelists today, we'll have the session speakers from this morning, but I also wanted to again introduce Dheevatsa from the Meta team. Dheevatsa is a research scientist in our AI hardware software co-design team, and he actually works a lot with a lot of the presenters here today, as well as with the UCSB faculty in terms of optimization. So welcome Dheevatsa to the panel as well.
Thank you, Bharath.
Okay, so with that, let's start with the panel discussion. And again, the goal of this panel is to kind of take the themes from this morning and then see what may be, and brainstorm around what may be some opportunities for the IEEE lab to focus on going forward in order to enable the green AI theme that was laid out by John in the start of the discussion. So maybe I'll start off this with an end user perspective, and maybe so I'll start off with this being directed more towards Dheevatsa and Cliff. We talked about some of the trends in hardware being not as favorable, even though there is some line of sight into the end of the decade, as Frank alluded it to. What are some of the things from a software perspective, from as end users, who you guys think are opportunities for collaboration and focus going forward?
Yep. Do you want to go take a shot at this, Cliff?
I might fail to tie this into the green theme, but I think the software challenge for accelerators and for neural networks is huge and open and transformative. I've drunk the neural network Kool-Aid. I think that the neural network machine learning revolution we're in the midst of right now is a better data-driven decision-making process. And what part of our economy is decision-making? All of it is, right? So if you have an if and else in your code and you wish you had a good branch predictor, I got a better answer for you. I don't have an answer that's economic right now, but I suspect that like we're going to come full circle down to a nanosecond level with machine learning techniques. We already have them with perceptron branch predictors. But aside from that computer architectural thing, I feel like we're going to rewrite all the software on the planet. So from that software perspective, like what we have today in GPUs and TPUs is still too hard to use, too far away, too unseamless. And so, I don't know, sorry, it's not the green answer. I feel like it's more the transform the economy answer. And maybe the better decision-making does turn back into greenness in the way that we more efficiently operate our data centers or shift load around the world and so forth. That's almost second order compared to we're going to rebuild all the software. And I'll pause there and say, Dheevatsa, your turn.
Yeah, no, I think you got I completely agree with what you said, right? So I wanted to kind of present a more practitioner approach to this. We talked a lot about hardware, and I think there are a lot of experts here who are actually doing the hardware here to kind of present this. But when we talk about software has so many levels, right? When we talk about software, it's the actual compiler, the code that runs it, on these kind of accelerators. There's software that takes care of actually the models. The models themselves are software, right? I mean, there's a blurring line between algorithms and software, and especially for folks like Meta and I mean, I'm sure Google and other kind of hyperscalers, we have this other layer of software which kind of manages or administers everything else, right? Schedulers, managing the fleet and taking care of this. And it kind of gets lost in some of this, but I just want to bring that back into focus because they have a huge contribution in terms of efficiency itself, right? We can build very efficient hardware. And if you don't have schedulers and kind of allocation, resource management to effectively use these things, it becomes really hard, right? And it's not an easy problem. Because of the nature of the beast, we're building heterogeneous fleets and we have to kind of manage, this becomes more of an extreme bin packing problem where we have to make sure that we're kind of utilizing these things in the most efficient way. If not, all of the innovation that goes into building this hardware can easily get thrown out of the window, right? So I think I wanted to kind of bring focus to that. And that's actually a lot of effort that goes in. And I think this ties back to what you said, Cliff. And if you kind of expand this on from a data center, several data centers, this goes back to the entire way, how we look at it at the planet scale. But if you kind of drill down to what we can do at a data center level, I think this becomes very important, right? And one other thing I did want to kind of come back to, which is somewhat software adjacent. When we talk about models, we tend to take a look at the marquee ones, right? GPT-3, Roberta, or one of the DLRM, but it's not always the case, right? When we actually run these models, it typically more often than not follows a power law where we have like a long tail of models, which have very different characteristics. We design for something, it's very efficient, but these long tail of models, if we are not efficient there, we end up kind of losing a non-significant part of that. So I think we need to think about the entire spectrum. And this is where having flexibility, I don't think we can design for everything, but having flexibility, fine-grained flexibility to kind of turn down power everywhere, not just power gating, right? Across the board. And I think those kind of things, and then having software to manage that intelligently becomes very important. And I think these are the things that we need to kind of start thinking about as we start pushing forward on these hardware innovations.
Excellent. So we'll come back to this theme later on in this thing. So maybe now I want to kind of switch gears a little bit and focus on some of the technology providers, like and maybe direct this more at like Rob, Frank, Surendra, right? Obviously, you guys have talked through like how challenging it is to drive more and more of performance from hardware, even though there is some line of sight through the end of the decade. What are some of the key hardware innovations and perspectives where you think there can be stronger collaboration, let's say between like technology providers such as yourself and like the IEEE and academia, and for a mutually beneficial path? And so I'm interested in your perspectives on that.
Happy to start there. First, I just wanted to Dheevatsa. It's you're absolutely right, and I got to tell you how much time I spend on all of that, all of those data center level issues, as opposed to really cool architectural advances on AI itself. It's just it's an incredible management problem. So opportunities for improvements and innovation. It's really we run into the three roof lines again and again and again, and that's memory bandwidth, compute throughput, and communication bandwidth. And they will always have a different mix. We'll run into them at different times in an AI neural network, but they're all really important. So the more, the better throughput, the better latency, it's a win. It will be a win. It will be a win for something. And then the last that is sort of almost like a roofline is memory capacity. So there are certain models that are becoming gargantuan. We're having discussions with people where a model would be 100 terabytes in a few years. It's got to be stored somewhere. And in order to fit into the AI training or even inference, it has to be incredibly high bandwidth memory. And that's not DRAM. That's not normal DRAM. That's not normal SRAM. It's new memory that we don't have yet, frankly. Dense power packaging, as counterintuitive as this is, we actually get more efficiency, it seems, when we densify these things, because we reduce the communication lengths. We're able to get higher throughput from the hardware. We don't have to wait for all the communication to settle. So densifying these becomes a thermal and packaging challenge. And it is an extreme challenge, but it's one that if we find answers there, we're able to actually make more efficient, higher throughput platforms. Higher bandwidth optics would be a big win. So with the more, we've gone way past the industry standards on communication bandwidth, and we need orders of magnitude. I'm not asking for 10x, I'm asking for 100x higher throughput per fiber, whatever. And if that can be efficiently packaged on a single fiber, then overall it's far more efficient. I think, and then the last one is if you guys can figure out how we don't have to do work. I mean, the most efficient work you can ever do is the work you don't do. So please, give us suggestions on what we can avoid doing.
Excellent, Rob. So maybe switching to Frank.
And I mean, I would just, yeah, excellent. I agree. Excellent job. I mean, just hit on exactly, a couple of those points, the densification. I mean, that's an absolute area for innovation, near term. And precisely for the reasons that Rob articulated, if it's dense, then you don't have to transfer bits very far, and picojoules per bit, kind of get to the minimum that they can possibly be. As soon as we are less dense, we're dragging. It's going to be terabytes per second across SerDes. It's less energy efficient, right? So I agree. We got to push the boundaries on basically power delivery into a particular dense package, and power removal, is the other half of that equation. The higher bandwidth optics. I mean, HBM, per stack. What we're talking, terabytes per second. Optics, great for, hundreds of gigabits per second, but it's nowhere near where we need to be for the local memory bandwidth. And candidly speaking, it's not even in the range we need for just the interconnect we're talking about within a box. So I wholeheartedly embrace the idea that it's got to be like 100x what we're talking about for optics to actually be practical. And then there's the whole reliability, robustness at scale thing. I think Dheevatsa was referring to. Optics plays into that as well, right? I mean, reliability for that. I'm going back to the density thing. Current optical solutions are, I'm sorry, I'm not giving you exact values, but orders of magnitude higher size and power than what we can do with little chip-to-chip interconnect. So, in order to connect the dots on anything more than, I'll just call it the scale-out interconnect, there's got to be a lot of innovation. I think a couple other things, that I know the industry's working on, but we got to embrace these lower precision floating point formats, because that's easy low-hanging fruit for energy efficiency and throughput. And then, like Rob said, anyone that can identify the work we don't need to do, let's figure that out.
If any of you are thinking of skipping the afternoon session, I think Frank just explained why you need to attend the afternoon session. Because
I'm planning on attending it because optics is great, but there's just a bunch of practical things that have to happen before it's going to be deployed, other than let's just call it the scale out interconnect.
Right. I know Rob has a pretty interesting agenda that's put together around this topic. And I know they're going to dig deeper into how to get the 100x that you guys both asked for. So folks, please do stay back after lunch to attend that session. So Surendra, kind of switching to you, your thoughts? Oh, you muted, Surendra.
So adding to what Rob and Frank are talking about, right? Following on the Frank's talking about the lower precision floating point, I do see some research papers published on in-date training as well. I'm hoping, actually, I'm not an expert in that area, but I'm hoping that will come to fruition at some point. Otherwise, the amount of data that's moving through is just phenomenal, right? So the other thing I want to bring out is in terms of collaboration. Everybody working in these silos doesn't work very well. It's like we have a very good opportunity right now. Unlike the data center networks, which have grown over time, now we are at a certain size of the network, and it's more bounded. Even though you may think 16,000 nodes or 4,000 nodes is large, but it's not million nodes, it's not billion nodes, right? So there is an opportunity for us to understand and work the software and hardware together. By that, what I mean is, could you get more output of the current network, or the network that you think is physically feasible? You put in a petabit of network, but how much of throughput are you getting? Like, it goes back to my earlier statement on is load balancing, congestion control. All these things are very important, actually. So that's where I expect more collaboration. Like, can there be a software controller that actually helps the network so that the network is actually getting used much more optimally? Like, is there a software and hardware combination? The network doesn't have to work in a silo and then say, I'll try to figure out everything and I'll do everything. Can there be an SDN controller or something that works together with this one? The other one is actually, but back to that energy proportionality. I'm a big believer in that I think we need to design for energy proportionality. And even there, again, I think the software and hardware working together would help.
Excellent. So
yeah, I mean, I just pile on to that one. Before I was working on this, I was working on notebook PCs. So a couple decades ago, battery life was all about a death by 1,000 cuts. And so you had to save milliwatts here and there, basically. There's an analogy here. Honestly, the first thing in server land is just get the most performance. And so, there does need to be more, software innovation to help, and I guess hardware hints to help. But, in order to make the dynamic power management, more and more pervasive, more and more usable, it's got to be, it has to be thought through so that it doesn't become a bottleneck, I guess is the way I'd phrase it. So, just an anecdote, you have like, for example, a PCIe link between a CPU and a GPU. In a notebook PC, doggone it, you can like put that thing in a super low power state. In a server, are you going to do that? What about the latency to bring that link back? That's a problem. And I mean, so yeah, power management, it's death by 1,000 cuts. And I don't mean that. In this case, it's life by 1,000 cuts, but we got to go after all 1,000 of those cuts. There's probably some low hanging fruit that can be gone after, sooner rather than later. But it takes, kind of upfront focus, identifying those areas and then figuring out how we can programmatically make it not a bottleneck.
Yeah, I just wanted to kind of add to that, right? I completely agree with what you're saying, Frank. And I think it goes across the stack. And specifically, if you're looking at AI, I think we have this ability because the workload itself is somewhat of a deterministic nature. So you have some sort of an ability or an advantage here to actually go ahead and say, look, I know this is what's going to happen, at least for a large enough regime so that I can actually go do this without having to worry about the latency to bring it back, right? I think the application space offers us that unique opportunity, and being able to kind of think about it more reasonably, holistically, and leverage that is going to be a very fruitful endeavor, right? But again, there's a whole bunch of things that you can do.
Yes, I mean, like if at the AI application level, it was possible to tell the hardware, hey, we're going to work on some computation right now, and we're going to not do any communication for a little while, then you could save some power in that communication infrastructure, So I mean, I think if those types of things can be surfaced, like the hardware doesn't necessarily know what's coming next. We need some software to tell us what's going to happen next. And if there are finer grain hints on that, then there could be finer grain power management and power savings.
Actually, if I could add two thoughts that you guys have really made me think about. One is that I think Meta is actually several years ahead of the rest of the industry. While you have a focus on being able to manage the overall profile, run efficiently, get throughput per watt, and be able to modulate the power depending on the data center level, power delivery and stuff. Virtually everyone else is just, I want the most throughput per dollar. And occasionally it'll be, and it needs to fit in this power footprint. We as a vendor have been interested in power efficiency only in as much as that it enables us to do more, like to get higher throughput. If we save some of the energy, then we can burn the energy elsewhere. So we're going to burn it all. The second thing is I really agree that there's a lot of end-to-end optimizations that have to happen, and not particularly trying to make an advertisement or anything, but there is a very clear reason why NVIDIA bought Mellanox, and it was because we kept seeing this being a blocker, and as well as we worked with the company, we still couldn't get everything we wanted, and we couldn't integrate the entire top-to-bottom stack. I would argue we're not nearly as efficient as we could be yet, but we have seen gains from having that entire top to bottom control. So yeah, I completely agree with that. I mean, more and more, this is an end-to-end optimization thing.
Excellent. So I want to switch gears to the collaboration model that Surendra briefly touched about. But before I do that, I've been taking fervent notes as you guys have been speaking. So I wanted to maybe recap the top 8 things that I think I heard you all say and see if you guys all give me a thumbs up. This is what top of mind for you guys all right. The first one was densification of power and packaging. The second one was the optics at 100x or that kind of a pain point. The third one was around resource management at scale. While not glamorous, it's important to make things happen. The fourth one that Cliff pointed out was around the need for an upcoming entire software rewrite and things like that, which are going to have to be done in order to drive more efficiency. The fifth one was around reliability at scale. That's a different paradigm than what we've been used to. The sixth one was around continued numerical innovation in order to reduce the amount of data that flows through the pipe. The seventh one was around optimizing things around better load balancing, congestion control, and those kinds of things across the network in order to drive greater cluster level efficiencies. And then the eighth one I had was more around intelligent power management that avoids burning SerDes power and things like that based on workload profiles that drive greater efficiencies. So does that sound like the top 8 from the crew here?
Yeah.
I just have a tiny fine tune to add to the numerical point, which is I would broaden it from numerical to numerical and algorithmic. That absolutely, I want 8-bit floats and 8-bit ints and 2 bits and 1 bits. But I want half bit and 10th bit too. And how do you get that? You get it by sparsity. You get it by changing the algorithm. You get it by not doing the work. And there's no floor there at 1 bit, right? We can be smarter. So be smarter, please.
Excellent point, Cliff. Okay, so now let's switch to the collaboration model, and maybe on this one I want to start with Lei Li and Yufei if they're still here. I think I want to kind of maybe get a perspective of the challenges that the industry thinks are areas of collaboration. Maybe I want to get, in my window, I don't see Lei Li and Yufei. Are they still here?
Yeah, I'm here.
Oh, Lei Li is here. Okay, I don't see Yufei, but Lei Li is here. Okay, so maybe if some of these pain points that are being raised here as opportunities, can you maybe talk a little bit about the collaboration model that is either here or would need to be here in order for UCSB, IEEE, and all of you to be able to drive these kinds of things more effectively? What would be some of the collaboration models that you would think are required in order to make faster progress towards these pain points?
Yeah, I think so. Right now, certainly there's some disconnection between industry and academia. So since I was previously working at the industry, so at that time I also collaborate with professors in the university as well. I think one model could work very well is of course we have a large collaboration, that's good, but it's also good to have like specific concrete project and have team, like maybe one professor, one student at the university, and one PI or one leader researcher at the industry, so that they can define a concrete problem to work on. I think that's one. The other is for the deliverable. So what could be the deliverable? Well, in university, paper, of course, is important, but for company, paper is not that important. Paper, perhaps the patent or some code is more important. Software package is more important. Well, it might be better to have the end goal, not just producing the paper, but also producing some hopefully some open source package that both the industry can contribute and also the students from university can contribute as well. So together we can build something really useful, maybe useful for research, but also useful for multiple companies in the industry, multiple applications, and of course with the input from industry, with real application, with real test data, that will be a plus.
Okay, and maybe just kind of expanding this further, if Mark, you have your hand up, so go ahead, and Mark and John, if you want to chime in on your comments on this one also, please.
Hi, I'm Mark Abel. I'm working with Bharath and team to and Yufei and Lei Li and all the professors here think about how we do the AI collaboration. One of the things that the professors often ask for, in addition to what Lei Li laid out, is data sets, and workloads, so that, if you want to attack a particular problem with an algorithm, for example, right? I mean, knowing that the algorithm, and sort of, let's call them realistic workloads and data sets. So, and we understand about anonymization of, customer data and so forth, but being able to attack some real problems through that, through that lens often is pretty helpful for the software folks particularly, and even architectural, innovations as well. So John, you want to add anything?
No, I think you and Lei Li covered it. Obviously, the goals at universities and training grad students is different, but what we're looking for is working on the right problems and inputs, and certainly data sets and ability to do that as part of it. And frankly, having the results of what we do have some value. So if it doesn't influence all the major data center companies, then it's kind of not worth doing. So, so that's what I think today's workshop was all about. Along that line a bit, it sort of ties in a bit with the afternoon. I agree with Frank and Rob. I understand that optics has a long ways to go to solve what you really need today, but we're not going to see 100x improvement immediately, right, in one generation. So Rob Stone has some metrics about what's needed for the afternoon, in terms of what we want to get to. But before we lose all the folks, all the users in some sense on this end, I'd be curious, when do you see optics going like co-packaged? To me, that's sort of the big win in terms of removing SerDes and power and getting much, much higher capacity. But assuming that, we do get at least a 20x improvement, how soon will that happen? Does that happen immediately? I mean, the need is obviously there. So, and what are the stumbling blocks? Partly, obviously, it's power. Partly, it's density. Partly, it's reliability. But what are the biggest concerns you have?
For me, I think ultimately that's a long-term direction. For NVIDIA, we have such a tight cadence on new product rollouts, and they must come out so that we can get on to the next one, because the innovation cycle is so rapid here, that it would be very difficult for us to hold one of those products to get the the integration of optics working in that. Now, that's clearly something we would work on in the background, and once it was mature and ready, then we could integrate it. But we already take so many risks every day. That's something we would not integrate into our mainstream product planning until it was stable.
Yeah. So maybe I can add a little to that. Is I think depending on which tier they're talking about, it's already here today, right? It's like, so if you see the switches are becoming available with co-packaged optics, it may or may not be there at the first tier, which is like basically direct connect to the AI accelerator until AI accelerators themselves support it. But I think at the higher levels where you need the distance. So that's what I was showing the table, is that for shorter distances, what is most energy efficient may be different from depending on the distance. At certain distance levels, co-packaged optics definitely makes sense, and I think they're already starting to become available. And over time, I expect that they'll make inroads.
I'm sort of debating with myself what I can say. Google certainly uses optical, right? We have a long haul links and WANs and so forth, which are obviously optical. And then inside the data centers, there's some optical, which I should wave my hands about, but there are articles about how we use optical. And to some extent, I view the in-package jump as a cost and reliability question. Like how much, like we know what the cost of a standalone optical transceiver is, right? And you could stick that next to your TPU, or next to any other part of your data center networking, and there's an economics associated with that. If that moves on package, where does that change our density, our power delivery, and our overall cost? That's where it starts becoming engineering and deployment kinds of stuff. And when it becomes really interesting to us, where we might integrate on a package, I think NVIDIA and Google are already in the business of special purpose interconnect that's electrical, right? So maybe the optical question is not a matter of whether, but when. Like, what additional stuff do you get us? How much more bandwidth is it than we currently get out of our electrical things? I think to what Surendra pointed out on his lovely slide, which I covet a copy of, the distance is a big deal, right? You saw Rob's pictures and my pictures of pods. Like, how long is your physical pod? How far does your electrical span go, right? At some point, it becomes a pain point. Okay, I think that was sufficiently hand-wavy while sort of highlighting we want it. It isn't necessarily the transition to on-package that's the key thing. The question is sort of if you're designing a data center, a warehouse-scale computer, how do you best blend this in? And one of your highlight points was reliability. Like, how does this play with reliability? Definitely front and center for us.
So certainly including the optics and co-packaged optics is going to make, I think, a large reduction in cost for the system, but obviously that co-packaged chip is going to become a lot more expensive when you put 4 terabits of I/O inside that. So I presume that's acceptable, but I think overall the system savings and reliability improvement I think will be significant.
So I would encourage you to write the white paper. Like even write the workshop paper and then the conference paper saying, here's why this is going to cross over. Because maybe a confession, I feel like Google doesn't do things that look like research in the sense that professors and academics do research. We are incredibly what can we build now focused, and a small number of us look a little farther down the road. And then I go to things like DARPA meetings and think we're pikers. We're not aiming high enough. So I feel like to this collaboration angle, like we would benefit from vision from the academic world about, here's a potentially crazy seeming way to restack your data center, but it might actually pay off for you. And I think we can have the dialogue to say, here's something we can disclose to better ground your analysis. And so it might iterate a bit, but my day job is so much, what can I build now, that I think what ought I to be building is where there's a huge upside potential for collaboration.
Yeah. So Cliff, actually, Broadcom has a co-packaged optics switch. So maybe if there's a paper going to be there, then we can collaborate on that. And then
cool. All right.
And I think this afternoon, Manish will talk about Broadcom's co-packaged optics direction. So.
Actually, I'm really curious to hear what Meta would think about integrated optics and reliability and serviceability. For example, if we were to integrate in a GPU to get the connectivity off.
I have Rob here, Catherine here. Maybe they want to chime in on this one.
Maybe I can speak to that a little bit. And I'm really encouraged by the conversation we're having right now, because you guys are setting us up perfectly for the afternoon session. So thank you. Yeah, so I think as Surendra alluded to and others have mentioned, we see the first intercept for more tight optics and silicon integration as being networking. So that's co-packaged optics. And, Meta's been, along with others, helping the industry navigate to a broad ecosystem through using standards development organizations such as the OAF. And we also had a joint collaboration with Microsoft, which did some of the initial work to set that, future standardization track up. So I think that's our initial foray. And that's on the back of doing some, mid-board optical integration that could deliver higher levels of integration than we could achieve with traditional pluggable optics. And we're actually on our second generation of that right now. So we've already been investing pretty heavily in that direction. I think bringing it closer to the compute elements specifically and enabling us to disaggregate compute systems is something that we're looking really seriously at right now. It's an really active area of study. And I think we're going to be able to leverage some of the learnings that we get by, the stuff that we've done in networking to understand things like what are the required reliabilities that we need, what are the error models, and the link performance that we can support. And, and it may well be that there needs to be some give and take on both sides, right? The system architects who are designing these systems may need to comprehend the fact that you need different levels of IO hierarchy. And I think that's something that we're hopefully going to get into in a bit more detail this afternoon. But yeah, I think we're definitely supportive of this. We see it as being necessary, and we're along for the journey, and we're going to be a very active participant. Cool.
Can I? That was fantastic, Rob. I've got a yes and it's I think there's a misconception, a common misconception that, and it comes from the history of optics in telecommunications, which is just a completely different environment. And there's this sort of, this impression that you need to hire a PhD to go with the optics you're buying, or right? That they're special. And I think a lot of that comes from the volumes at which these were deployed. If you're doing a single transatlantic link, that's a very different world than, building it into your compute fabric as part of the system. So it's a complete paradigm shift. And all I want to say is, if you manufacture the photonics in high volume using a lot of the same processes that you do for the other parts of the silicon. We're still talking about silicon, I think, here actually, maybe augmented silicon. But it is actually more reliable when you build it that way. And so we just need to change that paradigm. I think it's in our heads.
Excellent. So not to steal further thunder from the afternoon session.
Hey, Bharath, I had a question pending here for 15 minutes. I'm wondering if we could take it.
Yes, this is the question on analog computing, and is that the one you're talking about?
Yeah.
Yes, I was going to switch to that. So Go ahead. Why don't you go ahead and ask the questions?
Sure. So there's a lot of efforts, research and companies, for non-traditional compute. And, their defining characteristic is, whether they admit it or not, is lower precision and typically constraints, topological constraints. And what I've been hearing this morning, that's just opposite of the direction that this stuff is going. But I just wanted to pose the question directly. Is it of value, and is there a sufficient set of applications that benefit from that, or that's really just not of value?
That's a big question. I don't know. It looks to me like Cliff has some thoughts there. Actually, I've had reason to think about this quite a bit, and even thinking about papers that get published and stuff, and I'm really mixed about it. I'm starting to settle in on very simple things like CNNs, tasks that that tend to be less sophisticated, but are massive in scale. Think some sort of object detection in surveillance cameras and something like that. I think there's a real home for it in those kind of applications, because you can absolutely live with those compromises. And getting the efficient throughput is good. As far as advanced NLP and stuff, it's really hard to see how you could ever make it work in some of those situations. And certainly something like DLRM or that, I just can't imagine how it could possibly work.
Dheevatsa, you want to add to that?
Yeah, I was going to add, we didn't talk a lot about programmability and the need for that, but if you look at it, I think there's not a model, right? These things continuously keep changing, and there's a lot of churn that happens, right? There is no one set thing and we can keep kind of churning it out, stamping it again and again. We tend to look at it from a very kind of a broad perspective, saying these are the characteristics. So that allows us to think about systems. But if you look at the actual ground reality, every day the models change, right? I think that kind of change or dynamicity, I think to support that, it becomes extremely challenging. And that is a necessity part of it. We are willfully ignoring it to make things simpler. I think it's more of a dimensionality reduction. But the actual problem, when you want to kind of deploy it, this is a real problem that we need to kind of deal with.
Actually, I'm kind of oversimplifying too, because I said ResNet, for example, and ResNet started with, 128 by 128 pixel image, and now most people I talk to who are doing ResNet are working on 4K images, right? And that radically changes the actual implementation of the network and how it operates. So yeah, even the same network changes radically over time.
Yeah, I think from a deployment perspective, I think this goes back to what Rob was saying. There is always the tension about, if you have to build a lot of data centers, then you want to get to the next gen hardware sooner, faster, and more predictable in order to ensure that it can happen at scale. And I think at least for the foreseeable future, that trend seems to be taking precedence, right? In terms of making sure that the capacity that is needed to serve the business need is prioritized. And that means more predictable technologies that are deployed at scale, keep the developers in a happy frame of mind. I think those kinds of themes seem to be taking precedence. But I think going back to what I think Cliff was saying, in terms of a vision statement of where things may change in the long run, when these things get more predictable. And so it may have a different bent from a standpoint through which these are looked at maybe 5-10 years down the road.
And one thing, sorry, I just wanted to add a little bit more, right, to what Bharath was saying and what I said earlier. So we talked about compute partition between training and inference. These are not set things, right? So if you look at it separately, there's something that's already trained and deployed and something that gets continually experimented with. If you look at with that kind of a split, and I'm sure Cliff might have his own numbers from how is it Google, this experimentation and exploration for the use of infrastructure for this is significantly higher, whether it's training or inference. This forms one of the major chunk. So, and if you look at the type of things we're looking for with the hardware, or kind of increasing, it's all towards increasing capability so that we can foster or enable this exploration, which is what kind of grows or feeds that growth for AI, right? So I think we are looking at it in kind of a retrospective view, saying, look, these models, which we know, but if you look at the current, if I take a split of the view that's happening today in our data centers, a large portion is experimenting with a whole new set of models to come up with the next GPT-3, the next DLRM, right? So that is what fuels all of AI, right? I think that is a core component, and that's why we built for capability here.
To jump in, I think analog is another paradigm shift.
Yeah.
We're in the midst of the machine learning paradigm shift on top of digital CMOS, and it's working for us. I can see the potential in the analog stuff. There's magic there. Not even bad magic. Like, you're absolutely right about the precision things and the reliability things. Like, do I have to have my circuit at just the right temperature for the analog to work? And there are things in analog computing, like rapid differentiation and integration, which are part and parcel of how we train and backpropagate, that could be transformative if you found the right way to get the rapid differentiation to turn into backprop. So analog then becomes the breakthrough technology. But I'm not going to be able to do that at Google because I don't understand enough about analog or electrical engineering or how the theory of actually training works. I know how to ask the question and say, I can see the potential. It is another revolutionary breakthrough on top of, my goodness, these models currently work. So with my academic researcher hat on, I want that work to happen. Yeah. When does it pay off? I have no idea, right? Do I think the analog startups are about to flip the world over? Super fun and interesting world. Likelihood, meh, I think. Some of the startups are saying stuff about differentiation, and I love that. Those, if you're gonna back some of the startups, those are the ones I would go for, rather than the ones that are saying I'm equivalent to 4-bit accuracy. Like the ones that are saying, let me measure my analog thing in terms of the old paradigm, I think are kind of solutions in search of problems rather than just a way of overturning the apple cart. So I don't
hear you giving, though, a pass to these guys and say, yeah, I love this analog differentiation, and you can do it to 4 bits of precision. I mean, I think you're saying, right, I'd love to have analog differentiation, but I still wanted 32-point floating point accuracy, which is a contradiction.
No, I don't care about question. I don't care about 32-bit floating point accuracy. I care about the capability that Dheevatsa was saying. I care about, can you build a conversational agent with it? Can you do superhuman recognition? Can you translate with poetry? Those kinds of capabilities are the things that we're investing in. So I think right now, yeah, there's a bunch of metrics, like can you be as accurate as the ResNet and digital stuff? And that's a tail chase, right? That's like trying to beat the neural network at what it's best at. I don't know what the AlexNet moment is going to be for some analog technology. I think that's higher risk, higher return, and the formulation that'll change our direction rather than chasing the existing revolution. Yeah. I hope that's both the right mixture of encouraging and it's going to be really hard for you to catch the current deep learning CMOS revolution in its current form.
I actually really like the ideas of analog, and I really like the ideas of in-memory. I'm waiting for somebody to show me why it's excellent. And I think somebody will, but I'm not seeing it yet. I was just going back to exploration and experimentation, and that's how you advance the state of the art in neural networks. And arguably those become better and more efficient, and then you deploy those at scale, but you spend a lot of energy on the investigation. Our product, our DGX, is aimed at innovators like researchers. And every time we come out with a new one, people ask us, well, why are you putting all of those resources in it? Why are you putting, you don't need this, you don't need that, right? And we just way over provision the machine because we know somebody somewhere is going to figure out how to use those resources. And after a year or two, they do. And then they have a very rational use for those resources. But at the time we launch the product, we have no idea what people are going to do with them.
All right. So I think we are at 12:30, and I wanted to kind of recap. So we identified 8 areas, right? I think we will try and summarize these and then see how we follow up on those 8 areas as we go forward into collab opportunities and focused engagements. And then clearly, to Lei's point, we need to figure out what's the right mix in terms of value, research papers, software, open sourcing, and what are the models through which these engagements deliver value. But I would say that we have a good foundation to use to build up through 2022 and beyond in terms of focus areas. So I want to, once again, it's not like you guys all had like free Fridays. You have had like pretty busy days, and you took the time and effort for the presentations and also spending a large chunk of your of your Friday AM with us. So I want to thank you all for your time today. And maybe I'll just pass it on to John and Mark if they have any additional commentary to add for this particular session. And then we'll pick up the interconnect session later on at 1 p.m., I believe.
Well, thank you, Bharath, and all the speakers. That was a really, really good session. And I do hope a lot of collaborations come out of this. So I think we have set the framework and certainly set this framework for the afternoon. Rob, do you have any last comments before we take a 30-minute break? We'll get together again at 1 p.m. on the same link.
John, may I say one thing? I want to not only say thank you, but also that we look forward to, one of the great things about working with Meta has been that they're very collaborative, not only with us, but with all of you and other folks in the industry. And we look forward to working not only with Meta, but with all of you. And we have students who are looking for internships. That's one great way of collaborating we talked about and so forth. Some really great folks across the gamut of expertise. So we look forward to working with all of you. And if you want to think about bringing students in, and of course, we're in that conversation with Meta, but of course, the rest of you guys as well. Thank you very much. Appreciate your time.
Thank you, folks. It was a great discussion. I thoroughly enjoyed it.
Oh, thank you.
Yeah, thanks.
Thank you so much.
Okay, thank you.
Lots of
Rob,
fun. Thanks.
in half an hour, 30 minutes.
Yep, I think we're really well set up for the afternoon and looking forward to hopefully addressing some of the challenges in the interconnect space that we've been teed up very nicely by the presenters this morning. So stay tuned for more.